Welcome to Sleepless Scientist, the channel where science meets serenity. Whether you're here to unwind, doze off, or just let your mind wander among the stars, you're in the right place. Tonight, we'll be exploring a question that stretches the imagination to its limits. How big is the biggest thing in the universe? Get ready to journey through scales that make mountains look like molecules and galaxies seem like glitter. Thank you for watching. And if by chance this video ends up keeping you awake rather than helping you drift off, I'm truly sorry. Don't forget to like, subscribe, and leave a comment about where in the world you're watching from and what time it is for you. Now, let's begin our journey into the immensity of everything. In our daily lives, we interact with objects on human scales, tables, buildings, cities. Occasionally, we stretch our thoughts to consider the size of planets or the width of the ocean. But those are mere dust particles on the map of the cosmos. To truly grasp the magnitude of the universe's biggest thing, we need to start from the smallest frames we understand and climb, step by step, up the ladder of size. Let's begin with a grain of sand. That grain of sand is roughly 0.5 millimeter in diameter. You could fit 20 of them edge to edge across a fingernail. It's tiny, but tangible. Now picture Earth. If Earth were the size of a grain of sand, then the Sun would be about the size of a ping-pong ball, roughly 100 times Earth's diameter. And the Sun, while massive compared to our home planet, is still just a fairly average star. In fact, it's not even in the top tier of stellar giants. Now, let's inflate our perspective. Meet Betelgeuse. This red supergiant star in the Orion constellation is so large that if it were placed in the center of our solar system, its surface would extend past the orbit of Jupiter. Betelgeuse has a diameter estimated at around 1.6 billion kilometers. That's more than 1,000 times the diameter of the Sun. It's a giant among giants, though even it isn't the largest known star. That title shifts from time to time as new measurements emerge, but candidates like U.Y. Scuti or V.Y. Canis Majoris have given Betelgeuse stiff competition. U.Y. Scuti, for instance, has a radius more than 1,700 times that of the Sun. That's so big that light itself would take over 7 hours to travel around its circumference. For comparison, light takes only a bit more than a second to circle Earth. But stars, even those that dwarf our own Sun, are just the start of the size game in the universe. From single stars, we go on to star clusters. These are collections of stars bound together by gravity, often forming intricate cosmic structures. Open clusters contain a few thousand stars, while globular clusters may host hundreds of thousands. But even these are mere pearls in a larger string, the galaxies. The Milky Way, our home galaxy, spans approximately 100,000 light-years across. It contains somewhere between 100 and 400 billion stars. These stars are arranged in spirals, arms, and a central bulge that glows with ancient starlight. If you traveled at the speed of light, it would still take you 100,000 years to cross from one end of the Milky Way to the other. That's the kind of distance that begins to elude any meaningful human comparison. And yet, the Milky Way is not unique. It is one of an estimated 2 trillion galaxies in the observable universe. Some of these galaxies are small and irregular. Others are majestic spirals like ours. Then there are the elliptical giants like IC 1101, once thought to be the largest galaxy in the known universe. IC 1101 stretches across about 400,000 light-years. That's 4 times wider than the Milky Way. It is home to perhaps 100 trillion stars. Still, we've only scratched the surface. Galaxies group together in clusters, huge congregations of galaxies bound by gravity. The Virgo cluster, for example, contains around 1,300 galaxies and lies about 65 million light-years from Earth. These clusters themselves are part of even larger structures. Superclusters. Our local group of galaxies belongs to the Virgo supercluster, which spans about 110 million light-years. But even superclusters aren't the end of it. They form web-like patterns across the cosmos, creating a structure known as the cosmic web. Imagine threads and filaments of galaxies, each one stretching for hundreds of millions of light-years, all connected in a sprawling network that outlines the vast, mostly empty voids of space. These filaments intersect at nodes, massive regions where thousands of galaxies congregate. One of the largest known structures in the universe is the Hercules corona borealis. Great Wall. This immense superstructure is a galactic filament over 10 billion light-years long. That means light, traveling at its absolute fastest, would take more than 10 billion years to go from one end of this structure to the other. Considering the age of the universe is about 13.8 billion years, that's staggering. It suggests the early universe was already forming such behemoth features. Just a few billion years after the Big Bang, this colossal structure was discovered by observing bursts of gamma rays, high-energy explosions that often mark the death of massive stars or the merger of neutron stars. By measuring the distribution of these gamma ray bursts across the sky and noting their distances, astronomers identified clustering patterns that pointed to the existence of the Hercules corona. Borealis Great Wall. It remains a subject of intense debate and study, because its size challenges some of our cosmological assumptions. In fact, the existence of such a massive structure may stretch the boundaries of what current models of the universe allow. But is that the biggest thing in the universe? That depends on definitions. If we define thing as a single object, then stars or galaxies are contenders. But if we define it as a cohesive structure, something bound by gravitational interactions, then these filaments and walls take the crown. Still, we can stretch even further, because beyond individual filaments and clusters, the universe itself is expanding. The observable universe, the portion we can see and measure, has a radius of about 46.5 billion light-years. That's not because the universe is only that old, but because space itself is stretching. When we look out into the cosmos, we're seeing light that has traveled for billions of years. But the objects that emitted that light are now much farther away than their travel time would suggest. This observable universe forms a kind of cosmic bubble around us, extending in all directions. Its total diameter is over 93 billion light-years. That's not the size of the universe itself, just the part we can observe. It's the actual universe. Could be far, far larger, perhaps even infinite. So if we consider the observable universe as the largest thing we can measure, then its size is the ultimate yardstick. Every galaxy, every supercluster, every beam of starlight we've ever detected fits inside that 93 billion light-year sphere. It contains everything we can possibly detect, and likely only a fraction of what exists. But there's a twist. The universe isn't a static, neatly organized place. It's dynamic, chaotic, and still forming. Structures larger than the Great Wall might exist beyond our observational reach. There might be other filaments, other webs, or even other bubbles, entire regions of space-time beyond our cosmic horizon. And then there's the speculative realm of the multiverse. If the universe is only one of many, then perhaps the biggest thing isn't even inside our own reality. But that's a rabbit hole best saved for another time. Zooming back in. From the incomprehensibly large, it's important to remember how we measure all of this. Distances in astronomy are gauged in light-years. But to truly study these structures, scientists use telescopes, redshift data, gamma-ray burst, distribution, cosmic microwave background radiation, and simulations that model the evolution of the universe. The sheer scale of these objects and structures is so vast that even our fastest spacecraft would take tens of thousands of years just to reach the nearest star, let alone another galaxy. It's easy to feel insignificant when faced with such immensity. But there's another way to look at it. The fact that a creature on a tiny planet orbiting an average star in an ordinary galaxy can contemplate and even begin to map the size of the universe is nothing short of astonishing. We're the universe becoming aware of itself, peering out into its own vast reflection. And so, from grains of sand to galaxy walls, the question of the biggest thing in the universe leads us on a journey through every level of cosmic architecture. It's a question with answers that change as our technology and understanding evolve. Today, the Hercules Corona, Borealis Great Wall might wear the crown. Tomorrow, something even grander may emerge from the darkness. As our gaze continues to stretch across the boundless tapestry of the cosmos, we come to realize that immensity is not confined to structures that glow or burst with energy. Some of the universe's largest entities are dark, cold, and nearly invisible. One such phenomenon that blurs the boundary between structure and mystery is the vast cosmic void. These are not merely gaps between stars or galaxies. They are enormous, sparsely populated regions of space that span hundreds of millions of light-years and appear eerily empty. The Boat's void is one of the most well-known of these. It's discovered in 1981. This void lies about 700 million light-years away from Earth and has a diameter of roughly 330 million light-years. If the Milky Way were placed at its center, the nearest large galaxy would still be hundreds of millions of light-years away. In comparison to galaxy-rich regions like the Virgo cluster, the Boat's void is like stumbling into a cosmic desert after traversing a bustling metropolis. And yet, even the Boat's void contains a few dozen galaxies, an echo of the universe's structural rules that no region, no matter how large or lonely, is ever truly empty. These voids play an essential role in the architecture of the universe. They are not anomalies, but integral features of the cosmic web. Matter clumps together in filaments and walls, and between those threads, these immense voids naturally form. Imagine a loaf of raisin bread expanding as it bakes, with the raisins representing galaxies. The dough stretches and bubbles form, thinning and creating pockets that swell into cosmic voids. The fabric of the universe, it turns out, is a delicate balance between clustering and absence. Though not solid, these voids count among the universe's largest defined regions. Some researchers argue they should be considered among the largest objects, even though their composition is mostly the lack of matter. In the context of scale, the absence of something can be just as staggering as the presence of something else. And in the grand scheme of the universe, these invisible giants are every bit as monumental as the luminous structures they surround. Now shift focus to the time dimension. The size of the biggest thing in the universe isn't just spatial, it's also temporal. The light we see from distant galaxies is ancient. In fact, we're observing those galaxies not as they are now, but as they were billions of years ago. When we look 13 billion light-years away, we are effectively looking 13 billion years into the past. That means the structure of the universe we see at such distances doesn't exist in the same form anymore. It's like reading a postcard from a civilization that may no longer exist. Astronomers have observed galaxies so distant that their light began its journey toward us when the universe was less than 1 billion years old. These ancient galaxies are small and often disorganized, the building blocks of the grand spirals and ellipticals we see closer to home. Yet they, too, participate in vast cosmic structures. When mapped, even these distant specks arrange themselves into filaments, nodes, and voids. The cosmic web is timeless in its pattern, though its pieces evolve continuously. Consider now the question of containment. What contains all of this? If the observable universe is a bubble of visibility, what lies outside that bubble? The answer is one of the most humbling concepts in cosmology. We don't know. There is no edge to the universe in the way a balloon has a surface. Space itself is expanding. This expansion doesn't push into existing space. Instead, it creates more space. Every point in the universe is moving away from every other point, and the farther apart two points are, the faster they recede from one another. This cosmic expansion gives rise to what's known as the cosmological horizon. It's the maximum distance from which light could have traveled to us since the beginning of time. Beyond that, the universe continues, but it's unreachable. Light from those regions hasn't had enough time to get here, and in many cases, due to the acceleration of cosmic expansion, it never will. These unreachable zones may contain more galaxies, more great walls, more voids, but they lie forever. Beyond our sight, what we see then is not the full universe. It's a bubble of perception within a sea of the unknown. The actual universe may be hundreds of times larger than the observable region, or it may be infinite. Infinity is not a size we can visualize. It's not just large, it's beyond large. It's unending. The universe is indeed infinite. Then not only is there something bigger than the Hercules Corona Borealis Great Wall, there's something bigger than anything we can possibly imagine. In a spatially infinite universe, the most enormous thing is not a wall or a void or even the universe itself, but the concept of replication. In an infinite cosmos with finite configurations of matter, it becomes statistically inevitable that identical or near-identical copies of everything, including us, exist elsewhere. Somewhere out there, maybe 10 to the power of 10 to the power of 28 meters away. There could be another Earth, not a parallel universe, not a mirror world, but another Earth built from the same particles, by the same laws, with the same history, simply because the universe is large enough to allow for it. This leads to the consideration of the multiverse, not as science fiction, but as a legitimate cosmological hypothesis. Some models of inflation, the rapid expansion believed to have occurred just after the Big Bang, suggest our universe might be one bubble in a frothy sea of universes. Each bubble may have different physical constants, different rules, and different structures. In such a scenario, the biggest thing isn't within our universe at all, but the collection of universes themselves, a multiverse potentially infinite in both number and diversity. While we can't observe these other universes directly, certain patterns in the cosmic microwave background, the faint afterglow of the Big Bang, have been proposed as possible hints. Cold spots, statistical anomalies, unexplained variations. These might be nothing, or they might be bruises where our universe bumped into another. It's speculation, but it's informed speculation, grounded in theories that attempt to explain the data we do see. Back in the observable universe, our understanding of size becomes not only a question of quantity, but of coherence. A galaxy is vast, but it's held together by gravity. A galaxy cluster is held by shared dynamics. A supercluster might stretch the limits of gravitational cohesion. But beyond that, structures like the Hercules Corona Borealis's Great Wall may not be gravitationally bound in the traditional sense. They exist as statistical anomalies in density, as patterns in the distribution of matter. They are patterns, not objects, and that makes their existence even more extraordinary. It's worth noting that the largest gravitationally bound structure known is the Shapley supercluster, located about 650 million light-years away. This structure is so massive that it influences the motion of galaxies in our local region, including the Milky Way. Like a giant gravitational magnet, it pulls on the cosmic fabric across vast stretches of space. The Milky Way is currently moving toward an even larger region of space called the Great Attractor. And even that is only a part of something bigger, the Laniakea supercluster, which contains the Virgo supercluster and several others, all flowing in a vast river of galactic motion. The name Laniakea comes from Hawaiian and means immense heaven. It spans over 520 million light-years and encompasses 100,000 galaxies. This name, chosen for its poetic magnitude, captures something essential about what we see when we try to measure the biggest thing in the universe: a sense of awe. The Laniakea supercluster, although large, is still just one branch in the sprawling forest of the cosmic web. When we map the distribution of galaxies on the grandest scales, what emerges is not chaos, but elegance, a fractal architecture of filaments, nodes, and voids. Each filament may contain hundreds of thousands of galaxies, and each void may span hundreds of millions of light-years. Together, they form a structure whose beauty rivals its size. To bring it back down to something relatable, consider this: if you were to shrink the Earth to the size of a pea and scale the rest of the universe down accordingly, the observable universe would still be several kilometers across. Even in miniature, the scale would remain utterly incomprehensible. The universe is not just big, it's layered in bigness. Every time we think we've reached a boundary, a limit, or a record, we discover something beyond it. And so, the answer to the question, how big is the biggest thing in the universe, is as elusive as it is mind-expanding. It's a question with many answers: stars, galaxies, clusters, walls, voids, the observable universe, the inflationary multiverse. Each is a candidate, each is larger than the last, and each makes us a little smaller in comparison. But being small is not a defeat. In fact, it's a badge of honor. From our tiny vantage point, we can chart the heavens, measure light from the dawn of time, and theorize about regions beyond our reach. Our instruments may be anchored to Earth, but our curiosity knows no bounds. The sheer act of wondering how big the biggest thing is places us in a league of our own. We are tiny, yes, but we are aware. As our voyage through vastness continues, it's time to refocus on a fundamental distinction: the difference between visible size and conceptual scale. While the Hercules corona, Borealis Great Wall, cosmic voids, and galaxy superclusters paint an awe-inspiring portrait of spatial immensity, there is a deeper complexity that lies not in length or diameter, but in mass and influence. The universe's largest things may not always be those that span the most kilometers, but those that warp space, bend time, and shape the very behavior of the cosmos. Consider the largest known single structure by mass, the El Gordo cluster, officially known as a CTCL J0102 4915. It's a galaxy cluster located about 7 billion light-years away, and its nickname means the Fat One in Spanish, a well-deserved title. This galactic beast weighs in at an estimated 3 quadrillion times the mass of the Sun. It's so massive that it's actually 2 colliding galaxy clusters in the midst of merging into one. Each of its components contains thousands of galaxies, and their collision sends shockwaves through the surrounding gas that can be detected in X-ray observations. Clusters like El Gordo are held together by gravity, but gravity doesn't just keep things bound. In large enough quantities, it does something far stranger. It curves the fabric of space itself. The greater the mass of an object, the more it warps the space around it. This warping leads to gravitational lensing, a phenomenon where light from distant galaxies is bent around a massive foreground object like a lens. This effect is visible in images captured by telescopes like the Hubble Space Telescope, where background galaxies appear stretched, duplicated, or ringed around clusters in strange arcs of light. These light distortions help astronomers map the invisible mass that lurks in the universe, because much of this mass isn't made of ordinary matter. We turn to one of the most elusive and fundamental mysteries in cosmology: dark matter. Unlike stars or planets, dark matter doesn't emit light. It doesn't absorb it either. doesn't interact with electromagnetic forces at all. But it has mass, and therefore gravity, and its gravitational pull sculpts the formation of galaxies, clusters, and the filamentary structure of the universe. Dark matter is the invisible scaffolding of the cosmos. It's estimated to make up about 27% of the total mass and energy content of the universe. For every star, every glowing gas cloud, every swirling galaxy that we can see, there is 5 times more dark matter lurking unseen. Without it, galaxies wouldn't hold together. They would spin apart like pinwheels in a storm. The largest structures in the universe, such as the Shapley supercluster or the Sloan Great Wall, aren't just impressive because of their visible components. Their true enormity lies in their hidden mass. It's like looking at an iceberg. The glittering tip is spectacular, but the submerged base is where the real substance lies. And in cosmic terms, dark matter is the submerged universe. Then, above even dark matter in its enigmatic vastness comes dark energy, the dominant component of the cosmos, making up roughly 68% of everything. It's not a form of matter or light, but a property of space itself. It's the reason the universe is expanding faster and faster, rather than slowing down under gravity's pull. This acceleration is a baffling discovery. One might expect that the combined gravity of all the galaxies, clusters, and walls in the universe would gradually decelerate expansion. Instead, it's as if some unseen hand is pushing the universe apart. The influence of dark energy becomes more significant the more space there is. As the universe grows, there's more room for dark energy to exert its influence. It's not a thing in the traditional sense. There's no blob of dark energy floating through space. Instead, it's thought to be an inherent property of the vacuum itself. That means the biggest thing in the universe might not be a structure or even a collection of structures, but rather the very space between things, infused with an unseen pressure that stretches the cosmos. As we return to the realm of galaxies, there's one final type of colossal structure to examine: galactic walls. The Sloan Great Wall, discovered in 2003, spans about 1.38 billion light-years and was long considered the largest known structure in the universe until the Hercules Corona Borealis Great Wall came along. These walls are not solid, but composed of billions of galaxies spread across immense distances, forming sheet-like structures that define the edges of vast cosmic voids. These walls themselves can consist of smaller structures nested within. Imagine a wall made not of bricks, but of cities. Each city a galaxy cluster, each district within those cities a collection of galaxies, and each building in those districts a solar system. The scale is fractal, recursive, and endlessly nested. From a bird's-eye view of the universe, a perspective we don't have but can simulate, the universe resembles a sponge. Not one made for your kitchen sink, but a multi-dimensional network of glowing fibers and hollow pockets. The glowing parts are filaments, streams of galaxies connected across the cosmos. The hollow parts are voids, regions where the density of matter is staggeringly low. It's a pattern that repeats, not just for aesthetic reasons, but because of the physics of gravitational collapse, fluid dynamics, and the evolution of matter in the early universe. These simulations, such as the Millennium Simulation and more, recently the Illustristing Project, allow us to build virtual universes with billions of particles representing dark matter, gas, and stars. When run on supercomputers for months at a time, these simulations give birth to universes that resemble our own in uncanny detail. By comparing these virtual structures to real observations, astronomers refine their understanding of what the largest things really are and how they came to be. The formation of such gigantic structures begins with small fluctuations in the early universe. In the moments after the Big Bang, tiny differences in density led to some regions collapsing into stars and galaxies, while others became voids. Over billions of years, gravity pulled galaxies into clusters, clusters into walls, and walls into the titanic web we observe today. That's how the universe became not just large, but organized on a grand scale. Even though these structures span hundreds of millions or billions of light years, the forces that shape them acted over timescales just as immense. A structure like the Sloan Great Wall didn't form in a single event. It emerged slowly from a gradual dance of gravity, expansion, and time. This is perhaps the most profound aspect of the universe's largest things. They are not only spatially vast, but temporally deep. Their existence stretches across epochs we can scarcely comprehend. Imagine a timeline of the universe 13.8 billion years in length. Place your finger at the beginning. This is the moment of the Big Bang. Now move forward 400 million years, and the first stars begin to form. Another billion years, and galaxies start to cluster. After 10 billion years, giant filaments like the Hercules Corona Borealis Great Wall are well established. Meanwhile, Earth has only recently formed, and life is just beginning its microbial stirrings. At this point, humans do not yet exist. Civilization doesn't emerge until the final flicker of this cosmic timeline, barely the last 0.01%. And yet, in that tiny window of time, we have managed to piece together a map of the largest structures ever known. It's a testament to the strange, improbable miracle of cognition in a vast and largely indifferent universe. Now zoom in again. The largest black holes, known as ultramassive black holes, reside at the centers of massive galaxies and can have masses exceeding tens of billions of suns. The largest yet discovered, TON 618, has a mass of around 66 billion times that of the Sun. It's so massive that its event horizon, its point of no return, would be more than 390 billion kilometers in diameter, or roughly 2,600 times the distance from Earth to the Sun. That's a single object larger than the diameter of our entire solar system. TON 618 isn't just massive, it's active. It's what's known as a quasar, a black hole that's gobbling up matter at such a rate that it emits unimaginable amounts of energy. From billions of light years away, this ravenous singularity outshines entire galaxies. If you placed it where our Sun is, Earth would be incinerated before lunch. And yet, even this monstrosity is a footnote on the grand scale. It warps its local space, devours matter, and pumps out radiation. But its presence is a single punctuation mark in the cosmic sentence that spans billions of light-years. The structures it lives in, the webs it threads, the voids it borders, these are the real giants. So how big is the biggest thing in the universe? It's not just one object or one wall or one cluster. It's a hierarchy of enormity. It's mass and distance and time woven together. It's visible matter surrounded by invisible forces, all organized into a structure so vast that it only becomes comprehensible when you stop trying to grasp it in human terms. Instead, imagine the universe as a symphony of scale. Tiny particles dance in harmony with galaxies. Voids give rhythm too. The web walls provide the chords. And dark energy stretches the score toward an endless crescendo. It is in this cosmic symphony that we find the biggest things, not as soloists, but as part of an intricate, unending composition. In the cosmic symphony of scale, it becomes increasingly clear that size is not just a measurement, but a manifestation of deep, layered complexity. The largest things in the universe are not simply the longest, the widest, or the heaviest. They are those that operate across multiple dimensions of magnitude, mass, volume, time, and influence. These entities not only stretch across billions of light-years, but also reach through billions of years of cosmic history and control the motion of millions of galaxies. But perhaps even more astonishing than the size of these giants is the pattern. in which they emerge, the hidden blueprint of the universe. This blueprint is most elegantly expressed through the cosmic web, a term that sounds poetic but is rooted in the cold, empirical data of astrophysical surveys and simulations. The Sloan Digital Sky Survey, among others, has mapped millions of galaxies, and the result looks eerily organic. It resembles the neural network of a brain, with filaments of galaxies acting like neurons connected by synaptic threads. The similarity is not just visual. Both systems are governed by the interaction of nodes and connections, feedback loops, and the self-organizing nature of complex systems. But the cosmic web isn't a structure in the traditional sense. It's not a physical lattice you can touch. It's a map of influence, a structure that emerges from the gravity of dark matter, the distribution of baryonic matter, and the expansion of space itself. It's the framework within which galaxies live and evolve, where voids expand, and where the largest gravitational interactions play out over eons. The visible matter in galaxies simply traces the dark matter that dominates the web, like dew outlining a spider's silk. To better understand the immensity of this network, consider that a single filament of the cosmic web can be over 1 billion light-years long and hundreds of millions of light-years thick. Inside that filament might be hundreds of galaxy clusters, each with thousands of galaxies, each galaxy with billions of stars. Multiply that by thousands of such filaments, and you begin to appreciate the full volume of the largest interconnected system ever discovered. And yet, the cosmic web is not uniform. It is laced with voids, gargantuan empty regions that seem to defy the density of surrounding space. The Eridanus supervoid is one such region, spanning over 1 billion light-years and containing significantly fewer galaxies than expected. Its discovery came from observations of the cosmic microwave background, where it created a cold spot, an anomaly in temperature that hinted at something missing in the structure of spacetime itself. Some have speculated that this supervoid might be evidence of something even stranger, such as a collision with another universe. While these ideas remain speculative, they highlight just how much of the universe's largest features remain enigmatic. Voids and walls alike challenge our understanding of cosmology, hinting at deeper laws yet to be discovered or confirmed. These immense structures also influence the motion of galaxies. Our own Milky Way, as massive as it is being pulled by gravitational attractions far beyond its immediate neighborhood. One such attractor is the Great Attractor, a dense region of galaxies around 200 million light-years away. But even this is part of a much larger structure, the Laniakea supercluster, in which our galaxy is just a tiny node. The galaxies within Laniakea are not stationary. They move through space in what cosmologists call peculiar velocities, deviations, from the general expansion of the universe. These motions are dictated by the gravitational pull of mass concentrations and the push of expanding voids. It's as if galaxies were boats on a vast ocean, drifting in currents created by the mass contours of space itself. Zooming out, we find that Laniakea is not alone. It neighbors other massive superclusters, such as the Shapley concentration, which may itself be part of an even larger gravitational basin. These immense collections of galaxies, each containing thousands of members, may represent the trunks and roots of the cosmic tree, stretching across billions of light-years and intertwining in ways we are only beginning to map. But why do such enormous structures form at all? The answer lies in the early moments of the universe. In the fractions of a second after the Big Bang, quantum fluctuations, tiny variations in energy, were stretched to macroscopic scales by the process known as inflation. These ripples in the density of matter eventually grew under the influence of gravity, attracting more matter, forming stars, galaxies, clusters, and superclusters. Thus, the largest things in the universe are the descendants of the tiniest possible fluctuations. From quantum noise came filaments, 1 billion light-years long. This connection between the smallest and the largest scales is one of the most profound truths in cosmology. It suggests that everything in the universe, no matter how vast, has a history rooted in the microscopic. The cosmic web itself is the fossilized imprint of the quantum foam, a structure born from randomness, sculpted by gravity, and preserved across cosmic time. Now consider the question of measurement. How do we know how large these things are? Astronomers use a variety of tools, including redshift measurements to estimate distance, gravitational lensing to map unseen mass, and statistical analyses of galaxy distribution. The cosmic microwave background, a relic of the early universe, provides a snapshot of the cosmos when it was just 380,000 years old. Embedded within that snapshot are the seeds of all large-scale structure. The Planck satellite and its predecessors, like WMAP and COBE, mapped the tiny temperature variations in the cosmic microwave background with extraordinary precision. These maps have become the cornerstone of modern cosmology, allowing scientists to model the universe's age, composition, and expansion rate. More importantly, they provide a window into the birthplaces of the universe's biggest structures. These observations tell us that the universe is flat, homogeneous on the largest age scales, and expanding at an accelerating rate. But they also reveal the fingerprints of the largest objects, the distribution of galaxies, the flow of matter, and the geometry of space all bear the mark of these colossal systems. It's like reading a crime scene from a single footprint. Except the footprint is 13.8 billion years old and stretches across billions of light years. In this way, the largest things in the universe are not just objects to be cataloged. They are tools for understanding everything else. Their size, their mass, and their distribution help define the curvature of space, the fate of expansion, and the overall geometry of the cosmos. Without the Sloan Great Wall, without the Boat's Void, without the Hercules Corona Borealis Great Wall, we would know far less about the universe's history and future. This leads to a humbling realization. The universe is not random in its enormity. It is structured, it is logical, and its largest parts are key to deciphering its deepest secrets. Every galaxy cluster that moves toward a gravitational basin, every void that expands in relative silence, every filament that tethers galaxies across unimaginable distances. These are signatures of an underlying order, a cosmic architecture governed by rules we are only beginning to grasp. But just as our instruments and theories have given us access to the large, they have also forced us to confront our limitations. There are regions of space from which light will never reach us, not now, not ever, because the universe's expansion is accelerating. These regions are effectively cut off from our influence and observation. The things they contain, no matter how large, are beyond knowing. This cosmic horizon acts like a bubble around our observable universe. At roughly 46.5 billion light-years in every direction, it defines the boundary of what we can see. But it is not a boundary in the conventional sense. It's a limit defined by time, light, and expansion. And just beyond that edge may lie even larger structures, bigger walls, vaster voids. Cosmic giants will never meet. The possibility of the unknown is perhaps the most tantalizing dimension of cosmic scale. As enormous as the structures we've mapped may be, they might only be the smallest fragments of a universe far vaster than our observations allow. It's not just that there might be something bigger out there, it's that there almost certainly is. The principle of mediocrity suggests that we are not in a special place in the universe. If our observable bubble contains structures that span billions of light-years, it would be strange if the rest of the universe didn't. And if the rest of the universe contains similar or even larger structures, then the true answer to the question of what is the biggest thing might be fundamentally unknowable, not because we lack the tools, but because of the laws of physics themselves. There may always be a horizon, a veil, a final barrier beyond which measurement, vision, and certainty break down. In this sense, the universe is not just vast, it is epistemologically vast. Its largeness is not just a feature of space, but a limitation of knowledge. The biggest thing in the universe might not be a thing at all, but the space between our questions and the answers will never reach. And yet, within this fog of unknowing, there is clarity. What we do know is vast. What we have mapped is monumental. What we have imagined through telescopes, simulations, mathematics, and intuition stands among the greatest intellectual achievements of any civilization. To contemplate the size of the universe's largest things is to engage in an act of cosmic humility and cosmic pride at once. Because in the end, the measure of the universe is not just in light years or solar masses or gravitational pull. It is in our capacity to imagine, to reason, to wonder. Wonder is perhaps the most fitting companion on a journey through such unimaginable scales, for as we inch ever closer to the largest things the universe has to offer, the terrain becomes increasingly abstract. The physicality of a wall of galaxies or a cluster of stars begins to dissolve into conceptual constructs. Boundaries blur, names become metaphors, coordinates drift into approximations. And yet, this is not a retreat from truth, but an expansion of what truth can mean when dealing with billions of light years, trillions of stars, and eons of galactic choreography. So let's linger on this idea of choreography, because nothing in the universe, no matter how large, exists in stillness. Everything moves, everything drifts, tumbles, swirls, or accelerates. Galaxies rotate, clusters collapse and merge. Walls shift with cosmic flows. Even voids evolve, ballooning outward as their contents evacuate under the pull of surrounding filaments. This motion, subtle on human time scales, is monumental across billions of years. It sculpts the largest objects in the universe, like invisible hands. One of the grandest of these motions is the flow of galaxies toward what has been dubbed the dipole repeller. While the great attractor pulls our galaxy and thousands of others in one direction, the dipole repeller appears to push from the opposite side. These are not literal pushes and pulls, but gravitational effects generated by dense and underdense regions of space. Galaxies, including our Milky Way, respond to these tidal flows. The entire Laniakea supercluster is moving as part of this larger cosmic current. It's difficult to grasp this movement because it doesn't have an immediate frame of reference. There's no universal compass in space, no center, no fixed background. Instead, motion is relative, and gravitational flows carve invisible highways. Across the cosmos, these flows hint at structures even larger than what we can currently map, regions of matter and emptiness that reach far beyond the visible edge of our universe. In this way, the largest things in the universe are not only spatially vast, but dynamically complex. They are not static giants, but evolving systems shaped by momentum, collisions, and the gradual consumption of matter. A galaxy wall may have taken billions of years to form, but it continues to change. New galaxies join its ranks, voids stretch its peripheries, and dark energy gradually loosens the gravitational bonds at its farthest edges. Take, for example, the fate of galaxy superclusters. While gravity once pulled galaxies together into clusters and clusters into superclusters, dark energy is now unraveling those threads. Over trillions of years, galaxies not tightly bound will be swept away from one another by the expansion of space. Structures like Laniakea may ultimately fragment, leaving behind isolated island universes in an otherwise empty sea. This long-term evolution underscores the ephemeral nature of even the universe's largest creations. Despite their size, they are not permanent. In the very distant future, after billions or even trillions of years, the most massive superclusters will fade from view. Not because they vanish, but because the space between them expands so quickly that their light can no longer reach us. They'll disappear not in a flash, but in silence. Even now, we see the beginnings of this cosmic isolation. Galaxies that once emitted light toward us are already slipping past our observational horizon. Every second, more of the universe becomes forever unreachable. This isn't an artifact of technology, but a fundamental feature of the cosmos, a kind of built-in solitude. The bigger the universe gets, the more of it becomes lost to view. This strange, poetic fading of the cosmos gives a bittersweet cast. To the largest things we can currently see, they are like fireworks frozen in mid-explosion, captured in our observations at a moment when they are still coherent, still connected, still present. But the show cannot last forever. Even the most enormous structures are constrained by the clock of cosmic time. To appreciate the sheer enormity of these structures in human terms, consider the volume of the Hercules Corona Borealis Great Wall. Spanning over 10 billion light-years, it contains billions of galaxies. If each galaxy contains 100 billion stars, and each star has a planet or two, we're talking about an estimated number of individual worlds so vast that trying to write it out would exceed the lifespan of a star. It's not just big. It's beyond enumeration. And yet, from this swirling cosmic canvas emerges another layer of scale. One that is often overlooked, but fundamentally essential to the story of size. Information. The universe isn't just made of matter, it's made of data. Every atom, every photon, every gravitational interaction carries information. And the largest structures in the universe carry the most of it. Each filament, each wall, each void encodes billions of years of history. The distribution of galaxies reveals the physics of the early universe. The motion of clusters records the effects of dark energy. The shape of voids hints at the nature of inflation. In this way, the biggest things in the universe are also the most informative. They are libraries of cosmic truth, written not in books, but in distances, densities, and velocities. Understanding these structures means decoding their data, mapping positions, calculating masses, measuring redshifts, and simulating their evolution. This is why some of the most powerful tools in cosmology are not telescopes, but algorithms. Simulations like Eagle, Illustris, and Bolshoi recreate the growth of structure from the early universe to the present day using trillions of data points. These virtual universes are tested against real observations. When they match, we gain confidence in our understanding. When they don't, we hunt for what we missed. In recent years, machine learning and artificial intelligence have entered the field, enabling new ways to detect patterns in the cosmic web. These tools can find subtle correlations across scales, helping to classify voids, trace filaments, and predict the behavior of structures we haven't even seen. In a way, our simulations are becoming partners in discovery. Synthetic minds exploring a universe too vast for human intuition alone. But simulations also reveal something unsettling, that the structures we observe today are just the middle act of a very long play. In the distant future, the cosmic web will thin. The voids will grow. The filaments will stretch and fade. Galaxies will burn out. Black holes will evaporate. The structures that currently dominate the universe's appearance will slowly dissolve. This ultimate fate, sometimes called the heat death or the big freeze, marks a final chapter where even the largest things become irrelevant. Over time, matter decays, motion ceases. All gradients of energy flatten out. What remains is an empty, cold, and dark universe. A cosmos stripped of stars, structure, and possibly even time. And yet, despite this distant and desolate destiny, there is grandeur in the now. Right now, we live in an epoch when stars still shine, galaxies still collide, and the largest structures ever to exist are still visible. We inhabit a privileged moment in cosmic history, one where light still travels across billions of light-years, and tells us of ancient walls, vast filaments, and enormous voids. This fleeting visibility is a gift. It allows us to study and marvel at entities so immense that they redefine the boundaries of what it means for something to be big. It allows us to look back in time across billions of years and see the universe not just as it is, but as it was and as it's becoming. And in this context, size becomes not just a metric, but a story. The biggest things in the universe are stories, written in gravity and light, unfolding across space and time, narrating the tale of a cosmos that grew from quantum tremors to galactic grandeur. From the tiniest subatomic particles to the largest filaments of the cosmic web, the universe is a continuum of scale. At one end lies the Planck length, a unit so small it defies comprehension. At the other lies the Hercules corona borealis, Great Wall and the observable universe itself, objects so massive and vast they defy physical intuition. But both ends are part of the same story. A story that begins with inflation, progresses through nucleosynthesis and recombination, grows through structure formation, and blossoms into the rich, complex, and enormous universe we see today. The final question is not just how big is the biggest thing in the universe, but how big can it get? Is there a ceiling to structure, a limit to connectivity, a final scale beyond which nothing larger can emerge? Some cosmologists think the answer is yes, that the scale of the largest structures is determined by the physics of inflation and the size of the observable universe. Others suspect that more discoveries await, perhaps just outside the reach of our current instruments. Still others propose that the very idea of biggest might be misleading, that in a fractal universe there is always something larger, something wider, something more diffuse, and yet more connected. Whatever the case, the search itself is the reward. Every map we draw, every distance we measure, every simulation we run brings us closer to the truth. And the truth is this: the universe is vast beyond measure, but not beyond meaning. The biggest thing in the universe is not just an object, it's a reflection of our drive to understand. It's the horizon of curiosity, ever expanding. And even as galaxies drift apart and voids stretch into silence, that desire to know, to see, to imagine remains. To know the size of the largest thing in the universe is to engage with a scale so immense that even metaphor begins to falter. Language strains, analogies collapse, and still the universe expands. We may chart its features, quantify its structures, map its motion, and simulate its evolution. But what we are ultimately trying to grasp is a reality that functions in magnitudes that lie permanently outside the human scale. The Herculean task is not just to observe, but to comprehend. And yet, humanity has always pursued what lies beyond the horizon. The urge to measure the unmeasurable has driven science, philosophy, and exploration since the first time our ancestors looked up and wondered if the points of light above them went on forever. In the modern age, the tools may be more precise: radio telescopes, particle colliders, deep space probes. But the goal remains the same: to understand where we are and how far where truly stretches. In that pursuit, one question continues to haunt the perimeter of all discussions about size: is the universe infinite? Infinity is not merely large. It is not the next step after very big or extremely big. It is the place where measurement stops being meaningful. An infinite universe would contain not just more galaxies, but more of everything. More walls, more voids, more copies of Earth. More versions of you reading this very line in slightly different circumstances. The observable universe, that bubble of space from which light has had time to reach us, is finite. It has a radius of about 46.5 billion light-years, giving it a diameter of roughly 93 billion light-years. That's the portion of the cosmos we can see. But that doesn't mean that space ends there. It merely means we can't look beyond that distance, not because of technical limitations, but because light from farther out hasn't had enough time to reach us since the universe began. If the universe continues beyond this horizon, and most cosmologists believe it does, then the actual universe could be vastly larger. Some estimates suggest it could be hundreds or thousands of times larger. Others hold that it could be infinite in all directions. If that's true, then the largest structure we've observed would be, by definition, only a local feature, an eddy in an endless ocean. In an infinite universe, the concept of largest becomes conditional. There might be larger walls than the Hercules Corona Borealis's Great Wall out there, far beyond our cosmic horizon. They would be forever invisible to us. Their gravity might never affect us. Their light might never reach us. But they could exist nonetheless. Structures spanning tens of billions of light years, each one dwarfing the last. And if the universe is infinite, then these largest things aren't rare. They're inevitable. In fact, in such a universe, every possible arrangement of matter occurs somewhere. Somewhere, there's a region with a wall twice the size of any we've observed. Somewhere else, a region with no galaxies at all. In an infinite cosmos, possibility stops being hypothetical and becomes mandatory. Everything happens somewhere. This brings us into the eerie realm of eternal inflation. According to this model, space itself underwent an exponential expansion shortly after the Big Bang. But unlike a single explosive burst, eternal inflation suggests that this process continues in patches, creating pocket universes, each with its own physical constants, laws, and structure. Our universe would be just one bubble in an endlessly frothing sea of space-time. Within this multiverse scenario, the largest thing is not within our universe at all. It is the inflationary field that births countless cosmoses. Each bubble might contain structures of its own, some similar to ours, some radically alien. One might be filled with nothing but black holes. Another might never have formed matter. Another might operate under physics we can't imagine. Of course, we have no observational access to these bubbles. Their existence is a theoretical consequence, not a measured fact. Yet the theory of inflation, which leads to this possibility, has made successful predictions. It explains the uniformity of the cosmic microwave background, the distribution of large-scale structure, and the apparent flatness of the universe. If its broader implications are true, then the biggest thing is not just big in space. It's big in a way that makes our entire universe a detail. It is at this point that cosmic scale intersects with cosmic humility. We are not merely small, we are likely not central. The Copernican principle, which has guided astronomy since Earth was dethroned from the center of the solar system, extends outward. The solar system is not central to the galaxy. The galaxy is not central to the local group. The local group is not central to the supercluster. And our supercluster is not the pinnacle of cosmic architecture. The trend is relentless. And yet, despite being nestled in a rather ordinary spiral galaxy on the edge of a typical cluster in an unremarkable filament, human beings have built a model of the universe that includes structures so vast they span a tenth of the observable cosmos. Our minds are capable of encompassing sizes that our bodies cannot survive near. Our instruments extend our senses across eons. Our equations simulate billions of years of evolution. We are small, but our reach is immense. This reach is aided not only by observation, but by imagination. Much of what we know about the largest things in the universe is not visible to the eye. It's inferred from redshifts, gravitational effects, background radiation, and subtle patterns in the clustering of galaxies. It's a cosmos pieced together from shadows, yet the outline is clear enough to reveal shape. These outlines are not static. New surveys continue to reveal new structures. The Dark Energy Survey, the Euclid mission, the Vera C. Rubin Observatory. All of these are designed to map the universe with greater precision than ever before. They will help refine our understanding of how matter clusters, how voids stretch, and how dark energy evolves. They may also help us understand the boundary between structure and noise. At what point does a group of galaxies stop being a coherent structure and start being a statistical artifact? Are the Great Walls true entities, or are they visual illusions, formed by patterns in our limited sample? These are questions not of scale, but of definition. Defining what counts as a thing at this scale is tricky. Is a wall of galaxies a single object, or a collection of smaller ones? Is a void an object or a region defined by absence? At cosmic scales, identity becomes fluid. A filament may contain thousands of galaxies, each with its own orbit, composition, and history. Yet the filament itself behaves like a structure. The lines blur between collection and singularity. This blurring extends to time. The largest structures also have the longest lifespans. Their history is not measured in centuries or even in millions of years, but in billions. The light we see from the edge of the observable universe began its journey before Earth existed. Some of the galaxies we detect have long since changed, form, or vanished entirely. We see not what is, but what was. And that means our picture of the largest things is always a portrait of the past. The Hercules corona borealis, Great Wall may have evolved dramatically since the light we see left it 10 billion years ago. It may have fragmented. It may have grown. It may no longer exist in its original form. We'll never know. We are forever looking into a cosmic mirror that only reflects history. This temporal limitation adds another dimension to the question of size. What we measure is not only vast in space, but anchored in time. Our measurements are time-stamped by the speed of light. Every observation is also an archaeology. In looking far, we dig deep. And in digging deep, we uncover epochs where the universe was younger, denser, hotter, and structurally distinct. The journey to understand the biggest thing in the universe is also a journey through time. To see the cosmic web is to see how the universe has woven itself into complexity. To see the Great Walls is to witness the outcome of billions of years of gravitational organization. To measure voids is to understand where galaxies failed to form. To observe quasars and black holes is to see matter pushed to extremes. And perhaps the biggest thing is the pattern itself, the way matter organizes, stretches, thins, and clusters. The recursive elegance of structure at scale. Like a fractal coast that reveals more detail the closer you look, the universe's complexity only deepens as you increase the zoom. From clusters to superclusters, to filaments and walls, and perhaps to metawalls and inter-supercluster rivers of galaxies. Structure builds on structure until comprehension stalls. In that stall lies the cosmic web does not just map distance. It reveals logic. It reveals a kind of self-similarity that stretches from small to large. This is the essence of cosmic architecture, that from the random chaos of the early universe came not only stars and galaxies, but order, hierarchy, and structure that spans more than 10 billion light-years. In that span, we find our largest known entities, not as standalone islands, but as parts of a vast interconnected reality that challenges the very notion of separateness. The universe, at its biggest, is also at its most unified. It is a thing of things, a one made of many, a structure of structures woven by gravity, time, and the unseen threads of dark matter. To speak of the universe as one immense structure composed of interconnected entities is to recognize the poetic symmetry that emerges from physical processes spanning billions of years. This is not structure imposed from above, but one that grows organically from the most fundamental principles: gravity attracting matter, expansion stretching space, and time allowing patterns to emerge. The largest thing in the universe may not be a single object, but a living record of how the cosmos has evolved from chaos into complexity. This evolution has been guided by a simple force, gravity. Unlike the strong and weak nuclear forces or electromagnetism, gravity operates over vast distances and affects all matter. Though the weakest of the fundamental forces on small scales, it dominates the universe on large ones. It is gravity that allowed gas to clump into stars, stars into galaxies, galaxies into clusters, and clusters into colossal walls of matter. Gravity does not act instantly. It takes time for its effects to spread, and on the largest scales, its influence is cumulative. Structures like the Sloan Great Wall and the Shapley concentration were not created in a single event, but are the slow consequence of gravity's quiet, unceasing pull. Across cosmic time, gravity sculpts, tugging galaxies into clusters, weaving clusters into filaments, and surrounding those filaments with vast, echoing voids. In this light, the largest structures are not just assemblies of mass, but the footprints of gravity's long patience. Each one is a map of how matter has flowed, gathered, and expanded. They are the signature of time itself, written across the tapestry of the cosmos. What's more fascinating is that this process of structure formation has left behind echoes. The universe still rings with the vibrations of its earliest moments. These are not vibrations in sound, but in density. Acoustic waves frozen into the fabric of space, known as baryon acoustic oscillations. These ripples began in the primordial plasma and left imprints in the distribution of galaxies we can measure today. These oscillations set a preferred scale in the universe, about 500 million light-years. That scale shows up repeatedly in how galaxies are spaced and how clusters are arranged. It's like a rhythm embedded in the large-scale structure, a cosmic beat that persists long after the music stopped playing. This rhythm influences the largest things in the universe and helps define how far structures extend before blending into randomness. And beyond randomness lies coherence. Cosmic filaments don't just stretch, they align. Observations show that galaxies along a filament often spin in similar directions. Their angular momentum is not independent, but influenced by the flow of matter along the structure. Even galaxy clusters can show preferred alignments, tracing the gravitational currents that shape them. These alignments suggest that cosmic structure is not just random clustering. It is directional. It has flow. It has memory. The largest things in the universe are not only vast in size, but in information. They encode direction, density, formation, history, and dynamic behavior. They are not merely where matter ended up. They are how matter moved and why it settled as it did. The interplay between matter and motion becomes even clearer when looking at the cosmic velocity field. This map of galaxy motion reveals vast flows like winds across space, streaming along filaments and draining into clusters. Galaxies fall toward attractors pushed by gravitational pull and the evacuation of surrounding voids. This movement forms the skeleton of the cosmic web, constantly in flux, yet preserving its general form across billions of years. It's important to remember that the light from these structures is ancient. A wall 10 billion light-years away is a wall that existed 10 billion years ago. The Hercules Corona Borealis Great Wall, our current champion for largest known structure, is not just far, it is old. The image we see is from an era when galaxies were still young, stars were forming rapidly, and the elements for life were just beginning to spread. If we could see that same region today, it might look entirely different. Galaxies might have merged. Clusters might have evolved. The structure we call a wall might now be something more diffuse, more fragmented, but we can never know. The light we see is the only light we will ever receive from that ancient version of the wall. It is a fossil of structure, preserved in motion and distance. Fossils are more than remnants, they are evidence. They allow us to infer the conditions of the early universe. The distribution of quasars, the presence of radio galaxies, the clustering of active galactic nuclei, all these data points form part of a larger puzzle, each one individually insignificant. Together, they reveal the contours of the biggest things. And as we peer into those contours, we find echoes not just of matter, but of thought. The very act of charting these structures reflects the cognitive architecture of our own species. Our brains seek patterns, construct models, test ideas. The structures we find are not imagined. But our ability to find them depends on a kind of cerebral structure that mirrors what we observe. The universe may not be designed for us, but we are, in a strange sense, designed to understand the universe. Our senses are limited, our lifespans brief. Yet we can contemplate entities so large they defy physical intuition. We can simulate the motion of dark matter over 13 billion years. We can model the clustering of galaxies over billions of light years. We can recognize that the largest thing in the universe is not one thing, but a layered, dynamic network of emergent complexity. This understanding leads us to the concept of cosmic topology. Beyond local clusters and filaments lies the question of overall shape. Is the universe flat, open, or closed? Does it loop back on itself, curve gently through higher dimensions, or stretch forever in all directions? Current evidence suggests the universe is flat or very nearly so. But flatness does not imply simplicity. A flat universe can still be infinite. It can still contain an uncountable number of structures. It can still support structures so large that light from one side may never reach the other. Not because of space's geometry, but because of time's constraint. Some speculative models propose a toroidal universe, a donut shape where traveling far enough in one direction would eventually return you to your starting point. In such a universe, the largest structure would not be a wall or a void, but the universe itself. Its topology would define its maximum scale. The cosmic web would then be not only a pattern in space, but a pattern shaped by space's very form. And yet, even these models are bounded by the observable. We cannot see the whole. We can only map the part we inhabit. The largest things we know are the largest things we've seen, but not necessarily the largest that exist. Just as ancient cartographers drew dragons at the edge of the map, so too must we imagine what lies beyond our cosmic horizon. Perhaps there are structures even grander than the Hercules Corona Borealis Great Wall, structures that dwarf superclusters, that span regions of space not yet illuminated in our surveys. Perhaps the largest structure is one we will never detect, a web of dark matter, sprawling through intergalactic space, invisible but enormous. Perhaps the largest thing is not a structure at all, but a process. The expansion of space itself may be the greatest entity in the universe. It defines the limit of what we can observe. It sculpts the fate of all matter. It stretches filaments, inflates voids, and erases connections over time. The expansion is not an object, but it acts upon all objects. It is, in a way, the canvas on which the universe paints its masterpieces. In this context, the size of a thing becomes less about physical dimensions and more about impact. What matters is not just how big something is, but how it shapes the cosmos, the gravitational footprint of a cluster, the expansion rate of dark energy, the distribution of matter by baryon acoustic oscillations. These are the marks of scale that matter most. The universe, then, is not a collection of static things, but a set of dynamic relationships. Mass relates to space, space relates to time relates to motion, and motion relates to structure. Everything is entangled in a mesh of cause and effect that stretches across billions of light years and billions of years. And within that mesh we find the largest things, not as objects floating alone, but as intersections of influence. The Sloan Great Wall is a place where gravity has woven many galaxies into one coherent shape. The Boat's Void is a place where gravity has failed to weave, leaving emptiness in its wake. The cosmic web is the stage on which these extremes are arranged, a balance of presence and absence, density and vacuum. So as we ask, once more, how big is the biggest thing in the universe? We do so not with a single answer in mind, but with a constellation of perspectives. The biggest in mass, the biggest in volume, the biggest in gravitational effect, the biggest in duration, the biggest in what it reveals about the universe itself. Each candidate teaches us something different. Each one reflects a different aspect of the universe's character. And together, they remind us that size is not just scale, it is story. As we explore further into the reaches of scale, it becomes evident that the magnitude of the largest things in the universe is not just a numerical marvel. It is a narrative. Each structure, whether a galactic wall or a yawning void, carries with it a backstory written in the language of cosmic evolution. These entities are not frozen snapshots, but dynamic characters playing out roles in a story measured not in centuries or millennia, but in eons and eons. Consider the Shapley supercluster, one of the most massive galaxy concentrations in the observable universe. It is situated about 650 million light-years away and contains more than 8,000 galaxies. Its mass is so great that it exerts gravitational influence over regions far beyond its immediate vicinity. Our own local group is thought to be affected by this distant mass subtly drawn toward it across hundreds of millions of light-years. This gravitational pull is part of the explanation for the peculiar velocity of our galaxy. Why it moves not only with the expansion of the universe, but also through it, drifting like a leaf caught in multiple converging currents. The Shapley supercluster does not stand alone. It is connected to other massive structures by filaments of galaxies and dark matter, part of the larger Laniakea supercluster. The name Laniakea means immense heaven in Hawaiian, and it is an apt description. This sprawling collection of matter encompasses over 100,000 galaxies and stretches more than 500 million light-years across. It is the region of space in which the Milky Way resides, and it, too, is a node within a far vaster system. The structure of the universe appears to be hierarchical. Smaller systems exist within larger ones, stars within galaxies, galaxies within clusters, clusters within superclusters. Each level of this hierarchy has its own internal dynamics, rules, and timescales, and yet all are connected by gravity, motion, and cosmic history. No system exists in perfect isolation. Each is part of a larger frame. But just how high does this hierarchy reach? When we speak of walls, structures like the Sloan Great Wall or the Hercules Corona Borealis Great Wall, we're approaching the current upper limit of structure as defined by observable matter. These walls are not uniform slabs, but regions where galaxies are unusually concentrated, appearing as thick bands in redshift surveys. The Sloan Great Wall stretches about 1.38 billion light-years, while the Hercules Corona Borealis Great Wall spans an estimated 10 billion light-years. These are not minor details. The scale of these walls presents challenges to standard cosmological models. The cosmological principle, the idea that the universe is homogeneous and isotropic on large scales, suggests that beyond a certain point, structures should average out. There should be no preferred direction or special locations. But massive walls like Hercules Corona Borealis press against that assumption. Their very existence forces cosmologists to re-express the definitions of scale and randomness. Are these anomalies? Are they flukes of galaxy distribution? Or are they hints at an even grander level of cosmic organization? These are not rhetorical questions, but active areas of research. New surveys with deeper sensitivity and wider sky coverage will either find more such structures reinforcing their validity or fail to do so, suggesting that current examples are statistical outliers. Yet even if they are anomalies, they are real. They occupy space. They affect surrounding matter. They emit light, albeit ancient, and they serve as waypoints in our cosmic map, a map that, even as it expands, remains incomplete. For each wall we discover, there may be another just beyond our horizon. For every void we map, there may be a deeper one still unseen. And the voids, those vast expanses of nearly empty space, are just as significant as the dense walls. The Boat's void, for example, is about 330 million light-years in diameter and contains far fewer galaxies than expected. It's a region so sparsely populated that it was once dubbed the Great Nothing. But this nothingness is not meaningless. Voids are dynamic, evolving entities. They expand as gravity pulls matter away from them and into the surrounding filaments. In this way, voids and filaments co-create each other, the presence of one defining the boundaries of the other. This interdependence brings us to a deeper understanding of size. The biggest things in the universe are not just big because of how much matter they contain, but because of how much space they structure. A wall is large because it organizes galaxies. A void is large because it creates separation. Scale is not only about occupation, but about influence. Influence, of course, requires interaction. And, on cosmic scales, interaction is governed by gravity, but modulated by time. Galaxies interact through collisions and mergers. Clusters interact through gravitational tides. Superclusters interact, or fail to, depending on the rate of cosmic expansion. The accelerating universe ensures that many potential interactions will never occur. Structures that might have merged billions of years from now are now being driven apart faster than gravity can reconcile. This cosmic acceleration, attributed to dark energy, imposes a limit on how big things can get. In a universe with no dark energy, gravity would eventually slow expansion, halt it, and reverse it. Structures would continue to grow as matter collapsed inward. But with dark energy in control, the opposite happens. Expansion accelerates, and the universe becomes increasingly fragmented. Large-scale structure becomes frozen. Walls, filaments, and clusters can no longer merge across vast distances. The structures that exist today may well be the largest that will ever exist. In this way, we are observing the climax of structure formation. We live in a golden age of complexity, a brief window in cosmic time when matter has formed intricate networks but has not yet been torn apart by accelerating expansion. In a few trillion years, the sky will darken. Distant galaxies will vanish from view. The cosmic web will unravel at its outer edges, and all that remains will be the local structures, bound clusters, and isolated galaxies. This eventual isolation is not melancholy, it is merely physical reality. The laws of physics, when extended over billions of years, predict not continuity but dissolution. And so, the largest things in the universe today are the apex of a long process, the final peaks, before the plateau of future entropy. What becomes clear through all this is that the largest structures are not static monuments, but episodes in a drama that is still playing out. Their size is momentary, not eternal. Their presence is conditional. They are defined not just by their extent, but by their participation in a cosmos governed by emergence, evolution, and eventual decline. To understand their full story, we must also consider their origins. These walls and filaments began as minuscule perturbations in the nearly uniform soup of the early universe. Slight differences in density, differences of only one part in 100,000, grew over billions of years into the immense structures we see today. This is the wonder of cosmic evolution. That from near perfection, complexity arises. That from simplicity, grandeur unfolds. The background radiation that fills the universe, the afterglow of the Big Bang, contains the fingerprints of these ancient seeds. Tiny temperature differences on this microwave map correspond to the density variations that seeded galaxies, clusters, and superclusters. This radiation is not merely a remnant, it is a code. It contains the parameters of structure. It tells us how the largest things in the universe were born. And so we return to the idea of narrative. Size is not only spatial, but temporal. The biggest structures are also the longest stories. They span from the earliest moments after the Big Bang to the still-forming present. They connect us to a history that began before stars existed, before atoms formed, before light could travel freely. In their current form, they embody the entire timeline of cosmic development. This time awareness adds a final layer to our understanding. The biggest things are not only the most extended, the most massive, or the most influential. They are also the most enduring. Their lifespans dwarf those of stars. Their transformations occur across spans of time that reduce all of human history to an instant. And yet, we, fleeting and tiny as we are, have managed to trace those lifespans. To map those structures, to place ourselves within this vast narrative. That act of placement, of contextualization, may be the most profound human achievement. Not because it reduces us to insignificance, but because it demonstrates that significance is not a function of size. It is a function of perspective. We do not need to be large to think large. We do not need to be ancient to contemplate eternity. We do not need to span light years to understand what does. We exist in a universe where the largest things are both terrifying and beautiful, both unreachable and comprehensible. And that, perhaps, is the most staggering scale of all. Not the distance between galaxies, but the distance between ignorance and understanding. As we stand in awe before the largest structures in the universe, another layer of significance begins to emerge, one that stretches beyond physical magnitude or temporal scale. It is the relationship between what we observe and what it means. Not only do these enormous systems redefine the limits of space and time, they also illuminate the deep interconnectivity between matter, energy, and perception. The question, how big is the biggest thing in the universe, turns inward. It becomes not just about structure, but about insight. For a moment, consider the paradox that these largest things in the cosmos are known to us at all. They are not close. They are not easily visible. Some span regions so vast that the light from one end has not had time to cross to the other since the formation of galaxies began. They reside in regions of space so far from us that their presence is understood not through direct imaging, but through patterns, statistical ripples across massive sky surveys, subtle shifts in the distribution of thousands of galaxies. This knowledge is not casual. It is hard-won. Each step of our discovery, each new map, each new telescope, each deeper look into the night sky has involved patience, precision, and the relentless pursuit of patterns in the noise. The Sloan Digital Sky Survey, which first uncovered the Sloan Great Wall, relied on the redshift measurements of over 1 million galaxies. The cosmic microwave background, with its whisper-faint echoes of structure formation, required satellite missions like COBE, WMAP, and Planck to extract usable data from a background signal that permeates the universe. And from those measurements, we extract scale, not just size in kilometers or light years, but scale in influence. A wall of galaxies does not merely take up space, it commands motion. It curves the paths of galaxies, governs the shape of surrounding voids. It acts as a gravitational landmark, altering the structure and direction of matter around it. These walls are sometimes likened to continental plates on Earth, slow-moving, shifting features that define the geography of their surroundings. But on cosmic scales, the analogy expands. These plates are hundreds of millions of light-years wide. And they're not floating on magma. They're embedded in space-time itself. Their motion is a combination of local gravitational pull and the large-scale expansion of the universe. And while continents drift apart over millions of years, cosmic walls recede from each other over billions. But perhaps even that analogy is too grounded. Cosmic walls are not boundaries in the way we usually imagine them. They are more like scaffolding, frameworks upon which galaxies hang. These frameworks are traced not only by luminous matter, stars, and gas, but by the more elusive architecture of dark matter. In fact, dark matter is essential. Without it, the visible universe would not look the way it does. Galaxies would not form where they do. Clusters would not gather. Walls would not rise. Dark matter, though invisible, makes up the majority of the mass in the universe. Its presence is inferred through gravitational effects, how galaxies rotate, how light bends. As it passes near massive structures, how clusters behave when they collide. Its distribution is not random, but structured. Simulations of the universe that include dark matter produce a web-like structure eerily similar to what we observe. They show filaments, voids, and walls forming naturally from initial density fluctuations in the early universe. This dark web, this unseen lattice of mass, is arguably the true architecture of the cosmos. The luminous matter we see is just the frosting on the cake. The brightest galaxies are mere specks compared to the immense halos of dark matter that surround them. When we speak of the largest things in the universe, we must recognize that much of their mass, perhaps most of their influence, comes from what we cannot see. This duality between the visible and the hidden, the known and the inferred, is at the heart of modern cosmology. We chart walls of galaxies, but know they are shaped by filaments of dark matter. We observe motions in space, but attribute them to the pull of dark energy. The universe is a canvas painted in visible light, but defined by invisible forces. And this makes the concept of scale even more remarkable. The biggest things are not only bigger than anything we can touch, they are made, in large part, of stuff we cannot detect directly. Yet, we measure their mass, we predict their behavior, we simulate their evolution across cosmic time. The simulations themselves are marvels of modern science. Projects like Millennium, Illustris, and Eagle use supercomputers to model billions of particles interacting under gravity. They recreate the growth of structure from the earliest epochs after the Big Bang to the formation of galaxy clusters, walls, and voids. These simulations do not simply confirm our observations, they explain them. They show how the largest things arise from the smallest differences in density. They demonstrate how dark matter clumps, how baryonic matter follows, how stars ignite, and how galaxies merge. What we find is that large-scale structure formation is not random, it is rule-based. Given the right initial conditions, the universe will naturally develop a web-like structure. Gravity pulls matter toward over-dense regions. Expansion stretches the space between them. The result is a cosmic landscape of interconnected features. Filaments, voids, walls, stretching across billions of light-years. But these features are not eternal, they evolve. Filaments grow longer, walls fragment, voids expand. Over time, galaxies run out of gas, stars burn out, and the energy gradients that drive structure formation diminish. We are living in a window, a brief interval when the universe is structured, bright, and legible. In the distant future, that legibility fades. The accelerating expansion of the universe will isolate structures from one another. Distant galaxies will vanish from view. The cosmic microwave background will redshift into oblivion. Eventually, even local galaxies may become inaccessible as dark energy pushes them beyond the limits of our reach. The universe will not contract, it will dilute. In this far-off epoch, the largest things may still exist, but they will be unobservable. They will no longer interact. They will no longer exchange light or gravity. They will become relics, sealed. In isolation, their grandeur will persist only in memory or in the records of civilizations capable of looking back, across eons, with tools refined beyond anything we now possess. But we are not yet there. We live at a time when the universe still speaks. It speaks in the motion of galaxies, the clustering of matter, the fluctuations in the background radiation. It speaks through the patterns of quasars and the alignment of spin axes. It speaks through the redshift surveys and the radio signals from hydrogen gas. And the message is clear. Structure is vast, complex, and interconnected. To catalog the biggest things in the universe is to trace the path of cosmic growth. It is to map the gravity wells carved into space by mass. It is to follow the footprints of time as matter coalesces and emptiness expands. It is, in a very real way, to hold the history of the universe in one's mind. And in doing so, we confront not just immensity, but humility. The observable universe is vast, containing an estimated 2 trillion galaxies. Each galaxy may contain hundreds of billions of stars. And yet, all of it, every atom, every photon, every gravitational interaction we can measure, is still just a finite piece of the larger whole. Whether that whole is infinite or not remains unknown. But even within the finite, the scales are staggering. The Hercules Corona Borealis Great Wall is not just a record holder in size. It is a monument to our capacity to detect patterns in chaos. To map it is to claim a kind of intellectual territory that even in the face of enormity, we can chart, we can measure, we can understand. It is this understanding, not just the structures themselves, that constitutes the true achievement. The walls are grand. The voids are vast. But the recognition of those patterns and the explanations for why they exist are the culmination of generations of observation, theory, and curiosity. We began with questions etched into the night sky. What are those lights? How far do they go? Do they end? And now, centuries later, we answer with walls that stretch for billions of light-years, with filaments that thread galaxies across space like beads on a string, with voids so empty they contain just a handful of galaxies in volumes that would otherwise hold tens of thousands. And still, we ask, is that the largest? Is there more? What comes next? Even after tracing the outlines of the most immense entities our universe has to offer, even after decoding their origins, mapping their interactions, and projecting their futures, the fundamental question lingers like a low cosmic hum. Are we done? Have we truly grasped the scale of the largest thing in the universe? Or, more hauntingly, are we just scratching the surface of something even grander, deeper, stranger than anything we've imagined? The observable universe is limited by light. We can only see as far as light has had time to travel since the beginning of the universe, about 13.8 billion years. But due to cosmic expansion, that horizon now sits at 46.5 billion light-years in every direction. This sphere, the limit of our vision, contains everything we can measure: 2 trillion galaxies, vast filaments of dark matter, enormous walls, ancient quasars, and cosmic voids. But beyond that bubble lies a domain we cannot see, a region potentially infinite in extent, governed by the same physical laws, continuing the same web of structure, perhaps featuring even larger clusters, even grander filaments, or more monstrous voids. Our instruments fall short not because of lack of power, but because of the absolute speed limit set by light and time. There may be a great wall twice the size of Hercules Corona Borealis out there, sprawling across a region of space forever, sealed off from our detection. If so, we will never know. This introduces a profound asymmetry. The universe we can observe is a data-rich map. The universe we cannot see is a blank expanse on the edge of our knowledge. That edge is not just spatial, it is epistemological. It is the hard line between what is knowable and what is not. And it is within this limit that we seek to define the biggest. The Hercules Corona Borealis Great Wall may be the current title holder, but it could also be a statistical anomaly. As our surveys grow in power and scope, covering more sky, peering deeper into the past, we may uncover structures that rival it, exceed it, or even challenge our assumptions about what can form in a universe governed by the known laws of physics. At a certain scale, randomness starts to blur into pattern. A billion light-year-long wall might seem extraordinary, but if such features appear more than once, if multiple walls of comparable size emerge, then perhaps they are not outliers, but normal. The definition of the biggest shifts with every new discovery. Every filament, every cluster, every wall redefines the scale of what is average and what is exceptional. This scale is not just a fascination for the curious. It is a test of our theories. If structures exist that are larger than models of cosmic evolution can account for, then those models must be adjusted. Our understanding of dark matter, dark energy, or inflation might be incomplete. The very fabric of space-time may behave differently than we currently assume. Cosmologists use these extremes to stretch and stress their models. Like engineers testing a bridge's tolerance with heavy loads, scientists look to the largest structures as tests of the universe's underlying physics. If those structures exist and behave as predicted, our models survive. If not, we revise. But in all our modeling, we continue to return to a key insight. The largest things in the universe are not solitary giants. They are components of a connected network woven through the cosmos like veins through a body. Their size is not only physical, it is systemic. The filaments don't just extend, they link. The voids don't just separate, they define. And this systemic nature leads to another revelation. Perhaps the largest thing in the universe is not a single wall or filament or cluster, but the cosmic web itself. A network of interconnected structures spanning the entire observable universe and possibly far beyond. This web is not a set of parts, but a single structure, vast, continuous, shaped by gravity and seeded by primordial fluctuations. If we accept that, then the cosmic web, this tangled, branching lattice of galaxies, dark matter and voids, is the largest thing we know. It is a structure with a spine of filaments, a skin of walls, and lungs made of voids. It is not one thing, but the sum of everything. The shape of the universe, the outline of its growth, the map of its matter. This web is still forming. While the early universe was nearly uniform, structure has emerged over time. Gravitational collapse continues. Galaxies continue to fall into clusters, clusters into superclusters. Filaments thicken, voids widen. The web is dynamic, a living, growing structure, at least for now. But one day, this growth will stop. Cosmic acceleration, driven by dark energy, will freeze the large-scale structure of the universe. Galaxies will move away from each other faster than gravity can bring them together. Structures will become fixed in place. Over unimaginable timescales, matter will drift apart. Stars will burn out, black holes will evaporate, and the universe will grow cold and dark. When that time comes, the structures we now consider the largest will remain only as remnants. Silent behemoths embedded in an emptying sky. They will persist as monuments to a time when the universe was dynamic, structured, and alive with light. And yet, despite this bleak eventuality, the present remains glorious. We live in a moment of clarity, when the cosmic web is visible. When galaxies are abundant, when structure is at its peak. This is our age of cosmic architecture. The ceiling of possibility is still visible. The lights are still on. Within this light, we measure, observe, and understand. We build telescopes that see through dust and distance. We launch satellites that map the sky with pinpoint precision. We write algorithms that trace structure through billions of data points. We simulate the birth of galaxies, the dance of dark matter, the evolution of walls and voids. And in doing so, we grasp what is truly vast, not just the distance between galaxies, but the scope of human perception. The largest thing in the universe may be physical, but the most astonishing thing is that we can know it exists. We are tiny. The Earth is a dot in the solar system. The solar system, a dot in the galaxy. The galaxy, a fleck in a cluster. The cluster, a node in a supercluster. And yet, from this speck, we look out and see everything. We comprehend structures that span billions of light years. We measure walls that dwarf imagination. We map voids so vast they seem to mock the idea of presence. This capacity is scale of another kind. A mental scale, an intellectual one. The universe has allowed us for a brief moment to see it not only as a place of stars and galaxies, but as a system of systems, as structure embedded in structure, as a tapestry whose threads stretch beyond all reach, yet remain within our understanding. So, how big is the biggest thing in the universe? It may be the Hercules Corona Borealis Great Wall, 10 billion light-years across. It may be the cosmic web, the interconnected filaments of dark matter and galaxies spanning the observable cosmos. It may be the entire observable universe itself, a sphere 93 billion light-years wide. Or it may be something we cannot see, beyond our horizon, waiting to be imagined. But whatever the answer, its true scale lies not only in its size, but in our ability to reach toward it, to imagine it, to model it, to understand it. Thank you for watching this video from the Sleepless Scientist channel. If this cosmic journey kept you awake, I truly apologize, but at least now you're drifting through the universe in your thoughts. Please consider liking, subscribing, and leaving a comment about where you're watching from and what time it is there. I always love knowing how far our curiosity stretches around the globe. And now, if you're ready, let's shift from thinking about impossibly large things to letting go of thoughts entirely. The next few minutes will be a series of relaxing ambient sounds to help you drift into the kind of peaceful sleep that even a quasar's eruption couldn't disturb. Sleep well, dream vast, and good night.